Space, the final frontier. Space travel. It has captivated humanity for centuries. The dream of venturing beyond Earth, exploring the cosmos, and unraveling its mysteries is a shared aspiration. But how do we navigate the vast emptiness of space? How do we propel ourselves among the stars? Space may seem like a vast empty void, but it is teeming with invisible forces that govern the motion of celestial bodies and spacecraft alike. From the graceful orbits of planets to the fiery trails of rockets, everything in space is in constant motion, dictated by the fundamental laws of physics. Our journey to understand space travel begins with the brilliant mind of Sir Isaac Newton. His laws of motion, formulated centuries ago, hold the key to comprehending how objects move in the cosmic dance of the universe. Newton's first law of motion, the law of inertia, tells us that an object at rest will stay at rest, and an object in motion will stay in motion, traveling at a constant speed and direction unless acted upon by an external force. In the vacuum of space, where friction is nearly absent, spacecraft can coast at incredible speeds for long durations, once set in motion. The second law of motion explains how a force acts upon an object's mass to produce acceleration. In simpler terms, the more massive an object, the more force is required to accelerate it. This principle is fundamental in rocket design, as engineers must carefully calculate the thrust needed to overcome a spacecraft's inertia and propel it into space. The third law, perhaps the most well-known, states that for every action, there is an equal and opposite reaction. This law is the bedrock of rocket propulsion. As a rocket expels hot gas out of its nozzle, the gas, in turn, exerts an equal and opposite force on the rocket, propelling it forward. Reaching for the star's propulsion methods. Chemical rockets, the workhorses of space exploration, exemplify Newton's third law. They burn a mixture of fuel and oxidizer in a combustion chamber, generating hot gas that is expelled through a nozzle at high speed. This expulsion creates thrust, propelling the rocket upward. However, chemical rockets are not very fuel efficient. They require a tremendous amount of fuel to generate enough thrust to escape Earth's gravity. This limitation has spurred the development of alternative propulsion systems, such as ion thrusters. Ion thrusters, unlike chemical rockets that rely on high-thrust, short-duration bursts, use electricity to accelerate ions, creating thrust. While the thrust generated is significantly lower than that of chemical rockets, ion thrusters are far more fuel efficient. They can operate continuously for years, gradually accelerating a spacecraft to incredible speeds. Section 4. The Gravity Assist, a Cosmic Slingshot. Navigating space is not just about moving in a straight line. It often involves leveraging the gravitational pull of celestial bodies, a technique known as a gravity assist. As a spacecraft approaches a planet, it gets pulled by the planet's gravity, increasing its speed. By carefully planning the trajectory, mission controllers can use this gravitational slingshot to alter a spacecraft's path and speed, sending it hurtling towards its destination with minimal fuel consumption. The Voyager probes, for instance, used multiple gravity assists from Jupiter, Saturn, Uranus, and Neptune to gain enough velocity to escape our solar system. This technique is a testament to the ingenuity of scientists and engineers who have learned to work within the constraints of physics to achieve extraordinary feats of space exploration. Section 5. The Future of Propulsion, Nuclear and Beyond. As we venture further into the cosmos, we need propulsion systems that are more powerful and efficient than conventional chemical rockets. Nuclear propulsion is one such technology that holds immense promise. Nuclear thermal propulsion, for example, could utilize the heat generated by a nuclear reactor to expel propellant at much higher speeds than chemical rockets, significantly reducing travel times. Another promising area is nuclear fusion propulsion, which would harness the energy released during the fusion of atomic nuclei. This technology has the potential to enable interstellar travel, allowing us to reach star systems light years away. These advancements in propulsion technology are not just about reaching destinations faster. They are about expanding the boundaries of human knowledge and exploration. Section 6. Warp drives and wormholes, science fiction or reality. But what about the ultimate dream of faster-than-light travel? Concepts like warp drives and wormholes, often relegated to the realm of science fiction, have captivated our imaginations. Warp drives, as theorized, would manipulate space-time itself, creating a bubble around a spacecraft that allows it to travel faster than the speed of light without violating the laws of physics. Wormholes, on the other hand, are hypothetical tunnels that connect two distant points in space-time, potentially allowing for instantaneous travel across vast cosmic distances. While these concepts are still highly theoretical and face significant scientific hurdles, they represent the boundless possibilities that lie ahead in our quest to unravel the mysteries of the universe. As we continue to push the boundaries of science and engineering, who knows what incredible technologies we might develop? Perhaps one day, the seemingly insurmountable barriers of space and time will be overcome, opening up a universe of possibilities for exploration and discovery.